Okay, here we are on page 2 where we're going to talk about counting. Real counting. Counting in a much quicker way than you've ever done before. How many outfits does a person who owns 5 shirts, 7 pairs of pants, and 11 pairs of shoes have? Yes, we're assuming they all match. You have 5 shirts, and each shirt could go with this pair of pants, so that's 5 times 7, and each outfit there could go with each of 11 different pairs of shoes. So that becomes 5 times 7 times 11. That's 35 times 11. That's 385. Look at that. That was a pretty quick counting. Next, how many different license plates can be made by 3 letters? So let's write that out. 1, 2, 3 letters. And so that's 26 options in each one. And then followed by 2 numbers. So that's 10 digits that could go there, 1 through 9, and then also a 0 and 10. So that one I'm going to need to pull out my calculator for. I'm not quite sure on that guy. So we're going to take 26 to the third times 100. And that is, whoa, that's huge. We have 1,757,600. 1,757,600. Wow, that was some quick counting. All right, let's do the next one. How many 5-digit zip codes are there in the United States? 1, 2, 3, 4, 5 digits, and we can have 10 options in each one of these. And so we use the multiplication principle and we get 10 to the 5th, or 100,000. Good deal. Number 4, how many different 8-character passwords, 1, 2, 3, 4, 5, 6, 7, 8 passwords, can be made if each character can be a letter or a number? So if this could be anywhere from A to Z and 1 through 9 or 0, then there are 36 options here and 36 options there. Oh, wow, look at that. That's 36 timesing itself. How many different times is that? 8 of them. So 36 to the 8th power. What does that equal? 36 to the 8th power. A lot. That's 2, 8, 2, and a bunch of different stuff. 1109, which this is trillion times 10 to the 12th power. So that's a great big number. So we've got times 10 to point, let's do that, times 10 to the 12th power. Big number, big number. All right, let's move to the next one. Number 5, how many different sandwiches can be made with the following choices if we choose one from each category? So we're choosing one of each section. We'll revisit this problem again when we get to choose 2 or 3. So 3 kinds of breads, and each one of those could have a different of 5 kinds of cheeses, 4 meats, 6 veggies, 7 sauces. And 3 times 5 times 4 times 6 times 7. Ooh, let's find out what that is. 3 times 5 times 4 times 6 times 7. And that's going to enter, hey, look at that, 2,520 different sandwiches. All right, number 6. Let's see what we get here. How many different ways can we show one card out of a 52 card deck to 7 students and then replace the card after showing? So that means the first student gets a possibility of 52 cards. The second student, because we replaced the card back in there, there are still 52 options. And then 52 to all 7 of them. That's 52 to the 7th power. Ooh, is this going to be big again? 52 to the 7th power. Not as big as it used to be, but that's still 1.02 trillion. 1.02 times 10 to the 12th. Still very large indeed. All right, number 7. How many different diagonals in a convex nonagon? Oh boy, this is going to take some thought. So I want you to think of a nonagon. There are going to be 9 of these, vertices all the way around. If you start at one of them and you start drawing diagonals, you can draw diagonals to everything but the 2 right next to it. So at this, you can draw 6 of them, because all except for these 3. Now if you start here, this guy is going to have the same thing, 6, 6, 6. However, when you get to this guy, you've already drawn one, so he's only going to have 5. And when you get to this guy, he will have had 2 of them already drawn, so 4. So you could actually do this 6 plus 6 plus 5, 4, 3, 2, 1, all the way around. Or you could actually kind of make your own little thing here where you say, wait a second, what if we did that? What if we took and drew all of these diagonals from this vertex, and then drew them all from this one, and all from this one, all of them, including the one that we already drew. So when we draw that guy, you've got one going one way and one going the other way. So we double counted, but if we draw them all, it's easier to count up. And if you have 9 times 6, each one of these has 6 diagonals that originate from it. However, by the time we do that, we will have drawn every diagonal 2 times. So divide by 2. And the formula that's going to come out of this is this guy. So you can see that every vertex can draw all but 3 of the diagonals, because you can't draw the ones next to it because those are the sides, and you can't draw to itself. So that's where the n times n minus 3, and then since we've drawn each diagonal twice, we divide by 2 to get the number of diagonals. So 54 divided by 2 is going to be 27. On this one, we can actually count them if we want to, but diagonals in a pentagon. According to the formula, it's going to be 5 times n minus 3 is 2 all over 2. There are going to be 5 diagonals. Now since this is a small enough one, let's go ahead and draw out what happens in this guy. So there's a pentagon, and notice what we do. I'm going to draw red. Notice that this guy, there are 2 diagonals that I can draw. And then this guy, I can draw 2 diagonals. Notice I can't draw it along the sides and to itself. So that's where the n minus 3 comes from. And so if I do a different color on each of these, so you can kind of see, if I go to this one and I draw 2 diagonals, notice I go there and I go there. And now, see if I can get a different color in there. This guy, I can draw that diagonal and that diagonal. And then the very, very last one, a good bright color in here, draws that diagonal and that diagonal. Now if you notice, every diagonal has been drawn exactly twice. So I drew 2 diagonals here, 2 diagonals there, 2 diagonals there, 2 diagonals there, 2 diagonals there, and that allowed every diagonal to be crisscrossed exactly twice. So if this were the case, this would give us 10 of them, but since they're all covered twice, we divide by 2, and that's 5. So that's actually what happened there, but that would be very complicated to draw out. So let's continue on using that pattern. Convex heptagon, 7 sides, so 7 vertices. Each vertex can draw 4 diagonals, and that will cover each diagonal twice. So divide by 2, we get 14. Diagonals in a convex octagon. So that is 8 sides, so 8 times 5 all over 2, and we get 20. Good. Number 11. This is kind of fun. How many different ways can you rearrange 9 books on a shelf? We start off with, so here are the 9 places on a shelf. 1, 2, 3, 4, 5, 6, 7, 8, 9. And notice what happens if we take these books and pull them off the shelf and we count, just like we did up here or here or here, how many different options can go into this place on the bookshelf? Well, there are 9 of them. And 9 of them, but notice we can't stick 9 books here because we just used one. So there are 8 options there. And now we've used 2 of them, so there's 7, 6, 5, 4, 3, 2, 1. So that is 9 factorial, that exclamation point. And our calculator, will that help us? Absolutely it will. There's 9, go to math, over to probability, down to, there we are, factorial. And that gives us 362,880. And that equals 9 factorial. Fantastic. Number 12, how many different ways can we mix up the 26 letters of the alphabet? Well, we got 26 different options, 26 in the first one, 25, 24, and we get 26 factorial. I think it's going to be a large number, but let's see what we get. 26, math, over to probability, down to factorial, enter. And we get, oh wow, that's a big number, 4.033. 4.033 times 10 to the 26th power. Wow, big number. All right, number 13, how many seating charts of 5 students can we make? And this is again asking how many different ways can we mess these 5 students up? And that's the shortcut that we get. And that's going to be 5 times 4 times 3 times 2 times 1. Let's go ahead and punch that in. 5, and then math, probability, factorial, 120. How many ways can a 5-card hand be mixed up? So if you get dealt 5 cards, 1, 2, 3, 4, 5, how many different ways can they mess themselves up? Well, 5 can go in the first place, 4, 3, 2, 1. Yeah, this is exactly the idea of why we're doing this section. 5 factorial. It's going to be 120. So anytime in the future when we ask the question, how many different ways can we mix up this? How many different ways can we mix up 1, 2, 3, 4, 5, 6 different letters? 6 factorial. That's going to be 6 times 5 times 4 times 3 times 2 times 1. That's 720. How many different ways can we rearrange 4 types of cheese? 4 factorial. 4 times 3 times 2 times 1 is 24. Alrighty, that summarizes everything we've got on the simple forms of counting with factoring and multiplication.